Hi guys. I'm gonna be honest, I woke up like 2 hours ago, but I did say I was gonna do this, and I didn't really have a lot to do other than say hi to some friends that just visited from A&M. So we're gonna go ahead and get started on this VC1 chemistry walkthrough because based on the YouTube, that was the most like the most wanted option. Okay. So C1, which of the following gases would have the greatest average velocity at 300 Kelvin? Okay, so important thing to remember for this is that formula for average velocity, or like our root mean square velocity, is gonna be the square root of 3RT over M, right? And in this case, T is our temperature in Kelvin, R is our ideal gas constant, and then M is our molar mass. And you can like honestly derive this pretty easily just from like the internal energy formula and just like kinetic energy. But this is the general idea. So we know that all the gases are going to be at 300 Kelvin. R is also a constant. So the molecule with the greatest velocity is just going to be the lightest molecule. Which I mean, like makes sense because our internal energy is like directly related to our temperature. They all have the same internal energy. So if you think about like kinetic energy being 1/2 mv squared, the lighter the molecule is, the faster it'll go. So if we do like all the molar mass calculations, let me increase the font here a bit. On the first one, we have two oxygen atoms, so that's gonna be like 32 like AMU. B argon, if I remember, should be 40 AMU. I think that sounds right. I just went P table. They have a periodic table on here, but yeah, like it's gonna be like 40 AMU. CH4 should be like 16. CO2 is gonna be like 44. And then SO3 is gonna be, I think, around 80, something like it's gonna be something pretty high. So our answer here is just gonna be C, methane, aka CH4. So that's problem one. Okay, problem two. What is the name of CO2O3? Okay, so first of all, important thing is that we have to recognize that we're dealing with a metal and a non-metal. We're not dealing with two non-metals, and for very obvious reasons, we're not dealing with two metals. So in the case that we have two non-metals, we want to use prefixes to describe them. So what's a good example of this? Uh, let's think here. Let me look at P table again. I can probably come up with something. Oh, like let's say like N2O5 or 4. Yeah, yeah, N2O5. So N2O5 is known as dinitrogen pentoxide. Di meaning two, and then this pent or penta meaning five. So that's how we would name it for two non-metals. But in this case, cobalt is a metal, so we're not going to be using prefixes, and this eliminates options E and D. Then, when we're dealing with transition metals, we have to consider their oxidation state. Because like for instance, if we had like table salt, for instance, which is NaCl, we just say it's sodium chloride because sodium is like an alkali metal that will always have that like +1 oxidation state. I think that's the best way to explain it. But in this case, we have cobalt, which is a transition metal that have multiple oxidation states. So we need to specify what its like kind of charge is, which eliminates A. So out of these two, we just need to figure out what the correct one is. Since this is a neutral molecule, we need the charges to cancel out. Each of the oxygens will always have a -2 charge. So the three oxygens carry a -6 charge, and our two cobalts need to balance that with a +6 charge, which means that each cobalt must have a +3 oxidation state. Hence, we have cobalt 3 oxide as the name of our molecule here. Yeah. C3, which term best describes the energy that increases as a matter becomes dispersed? This is just more of just kind of a definition question. And the answer to this one is going to be entropy. Entropy basically describes, in simple terms, the disorder of a molecule or like a substance or something. In other words, the more spread out a molecule is, the more entropy it's going to have, the more disorder it's going to have. And another, I guess, similar concept that's important to remember is that by logic, gases are going to have higher entropy than their liquid and solid equivalents. So here, enthalpy just kind of represents like heat energy in a sense. Free energy and spontaneity are kind of related concepts that relate to like how likely a reaction is gonna happen on its own. So for instance, if a reaction is considered spontaneous, it'll just happen on its own without like an any external energy needed. And the kinetics just refers to just like the movement or like just like in the general reaction of stuff. And if you've taken AP Chem, I mean that's like all just unit 5 stuff, like rate constants, activation energy, and so on and so forth. Okay, C4, what would cause us to proceed in the forward direction? So this is all just have to do with like Le Chatelier's principle and all that good stuff. Okay, so first option is what happens if we add I2? So you would think that if we add I2, we would have more stuff to like react with that can like go in this direction. However, we have to think about this in terms of like the whole what's it called? Like the rate constant? No, like the whole equilibrium constant formula. That's what I meant to say. So in this case, our equilibrium constant is gonna be equal to all our products, all our reacting products, our gaseous products and our aqueous products. So in this case, it would be like the concentration of HI squared because we have 2 moles of those divided by in this case, just the concentration of H2. And because diatomic iodine is a solid, it's actually not going to affect our rate constant, which means that even if we add I2 into this reaction, it won't continue, it won't like suddenly proceed in the forward direction. Now, if we remove hydrogen gas, we're removing some stuff from this side. So now what our reaction wants to do is that to balance it out, it's going to go in the reverse direction. Decrease some of this HI so we have some hydrogen gas still adding or like I guess just hydrogen gas to compensate. If we remove HI, then suddenly we have an imbalance on this side. So we're going to shift in the forward direction. So that makes us think C. Addition of argon gas. Since I believe it's just since argon gas is just not in the like reaction, there shouldn't be a reason for it to like suddenly affect the direction. So if anything, it should just not do anything. And then reduce temperature, since this is an endothermic reaction, as the change in enthalpy is positive, that means that increase in the temperature is going to be more favorable towards the forward direction. If we reduce the temperature, it's going to go in the reverse. So thus we conclude A and D don't do anything. E and B are going to make it go in the reverse direction. So that means that C should be yeah, C will be our answer on this one. Okay. C5. What is the percent by mass of O in CuSO4 dot 5 H2O? So copper 2 sulfate pentahydrate. So in this case, the percent mass of oxygen or the percent mass of any element in any compound, we can just take the mass of all the oxygens and divide it by the molar mass of the whole thing. So in this case, our oxygen, we have 4 oxygens in the copper 2 sulfate part and the 5 oxygens in the pentahydrate part. So that's a total of 9 oxygens. I think it should just be 16. Yeah. So yeah, well, it was 15.99, same thing. Okay. And then we're gonna divide this by the total molar mass. So copper is 63.55 plus sulfur, which I believe is 32.07. You could be like ever so slightly off on these, it'll be close enough. Plus 4 times that 16. So that's our copper sulfate. Plus 5 times the mass of water, which I know is just 18.02, 16 plus the 2 hydrogens. And we end up getting 57.7% as our percent by mass of just the oxygen. So that one's pretty easy. And I guess just important thing to know is that, yeah, you can like jump all over the place. Like for instance, when I get to 7, you'll realize that that one's also like a piece of cake. So don't get discouraged if you see like 1 or 2 problems that you don't know immediately. Uh, Experiment is conducted using a zero point 0.1 molar reagent, and the reaction takes 5 minutes. But when we double the concentration, it takes 10 minutes. What describes this phenomenon? Okay, so in A, we're saying that the particles move slower, so the reaction takes longer. And although the particles moving slower would mean that the reaction takes longer, it doesn't really make sense for the molecules to suddenly slow down just because we added more. So A is probably incorrect. B, the activation energy is being met more quickly in the first trial. This also doesn't really make any sense. It shouldn't really make a lot of sense that like the molar concentration increasing suddenly like causes the activation energy to be reached slower and just a like, whole energy peak. C, the reaction is second order in both trials. Um, Hang on, I need to like double check the formula for this second order reaction. But like this should not change like anything at all. If we have Yeah, so here it says, if you kind of just like write out the whole logic, that our half-life formula is going to be equal to the reciprocal of our rate constant times our initial concentration. And it says if we have a bigger concentration, we should have a smaller half-life, which means that adding more should actually take less time. So C is not a valid response to this. D, there are more reactant particles in the second trial, which take a longer time to collide and react. If they do take a longer time to collide and react, that would explain why it suddenly takes double the time. So this could be our answer. And then E, the initial rate remains unchanged in both trials because the ratio of molarity to time is the same. There shouldn't be a relation between the molarity and how much time it should take. Like in this sense, so E should be wrong. And out of these, D just makes like the most sense. Like you add more molecules, they're gonna take more time to react. Okay. C7. How many electrons are in lead 207, the ion of lead 207? Okay. So we just recall through here that if lead has 82 protons, then in a neutral atom of lead will also have 82 electrons. But this is a plus two cation of lead, which means that it's going to have two less electrons. Two less than that's going to be 80 electrons. And the way you can double check this is think that, okay, if I have 82 protons and 80 electrons, each of the protons and electrons will cancel each other out, except for the two protons that are left. So we have a net plus two charge. C8. So this is just electrolysis with Faraday's constant. So idea here is that we want to deposit 2 grams of nickel using an NiCl2 solution. Okay, so what we want to do is we want to check, okay, how many moles of nickel is 2 grams of nickel? So the molar mass of nickel is 58.69. So this represents the moles of nickel that we need, right? Now, if we write out like the kind of reaction for this, we have that this nickel has like a plus two charge on it. So we need to like run 2 electrons for every 1 atom of nickel to like plate it. So, or another way to phrase that is that for every mole of nickel, we need 2 moles of electrons. So if this is the amount of moles of nickel we have, then this is the amount of electrons that we're going to end up needing. Now, using Faraday's constant, which should be listed somewhere. Oh, right here. So Faraday's constant states that for every mole of electrons, it has a total charge of 96,485 coulombs, right? And you can honestly just derive this on the spot if you didn't know this, just using Avogadro's constant plus like 1.602 times 10 to negative 19 like coulombs per electron. So if we have this many moles of electrons, multiplying it means that this is how many coulombs we need, right? And if we have a 5 ampere current, mean 5 coulombs per second, divide this by 5 gives us the number of seconds. And then thus we have 22 minutes as our answer. 8 is C. Yep. Number 9. Which of the following molecules has a linear molecular geometry? Okay. So starting off with H, here, I'm gonna write each of these, so this may take a while. Okay, so yeah, and honestly, feel free to just skip this a bit. I'm just gonna be drawing for a sec. Oxygen should just be like this, and these are all gonna be drawn linear originally because I don't want to draw them bent to start off with if they don't end up being bent. So if SO2, we have NO2 minus, then this just means we have an extra electron. And then lastly, we have ICl2 minus. Okay, so general idea is that if this is going to be a linear molecule, we can't have any extra electrons on our central atom because if we do have extra electrons, that would mean that those electrons are going to cause repulsion by Vesper theory and then thus change the molecule structure from like linear to some form of bent. So in this case, we start off with H2S. So sulfur has six valence electrons. The hydrogen you have one. So there's total eight valence electrons here. So what we're going to do is we're going to start off by drawing. We're going to start off by trying to make everything have uh let's say each thing have like a full orbital. So that's two electrons for hydrogen. Since there's going to be like two electrons in this bond, we say that this has two. We say that this has two. And the sulfur has a total of eight. So this forms a full what's it called? Wait, I'm double check I'm doing this right. Yeah, so each of these have a full octet, and since all these have a full octet, there's no adjustment that needs to be made. So what we notice here is that we have like kind of linear structure, but these electrons in actual space are going to cause it to bend. So that means that H2S is going to be non-linear. If we look at our second one, we have ozone, which is O3. Each O has six electrons. So if we draw out our structure, actually, I'm gonna start using lines here. Each of these lines, just think about it as two electrons. I wouldn't recommend this if, especially if you're like learning this for the first time, but I do just use this just because it's a bit easier to draw out than like actually drawing the lines, especially or drawing the dots, especially because I don't have I'm using this on trackpad. So now each of these have eight valence electrons. If we talk about the count the total number of electrons, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 20 electrons in our diagram, but our molecule only should have 18 electrons. So what we're going to do here is we're going to take one of these valence electron pairs and then one of these here, and then we're going to replace it with a double bond. So now this still has eight, this still has eight, this still has eight, and now we have 18 electrons, right? And what we notice here is that it's kind of a similar idea where we have the linear structure, but we have this extra electron pair here, which is going to cause it to bend. If we look at option C, sulfur dioxide, we have six sulfur electrons and each of the oxygens have six electrons. We honestly don't even need to draw this out because since it's going to be 666, this is literally going to be the same structure as the ozone, and thus we still have bends. If we look at NO2, each nitrogen should have five electrons, if I remember right. Yeah, five electrons. Each of the oxygen have six, and because of this negative charge right here, we have an additional electron. So five plus the two sixes plus an additional one gives us 18 total electrons. And for the third time, we have the exact same structure. We have something like this, where we have that extra electron pair on the nitrogen that causes this to be bent. So that makes us think our last one has to be the answer, but of course we should make sure. Iodine and the chlorines each have seven electrons. That's 21 electrons total, plus this electron here, because this is like a polyatomic ion, this is 22 electrons total. So let's go ahead and draw out this thing. Should be doing this right. I'm gonna go ahead and double check real quick. Yeah, because the question is, which was a linear molecular geometry? Interesting. Okay, okay, okay. I see why. This is like a bit of a trick. Okay, so if we count the electrons here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs, right? So that's 20 electrons. So we need to add an additional pair. And since iodine is one of many molecules that allows us to have like an expanded orbital, and these are like majority of molecules that start from phosphorus, I believe. Phosphorus or sulfur is, I think, the first point. So we have an electron here. So what we're going to end up having is we're going to actually have three electron pairs right here. Okay, so now we're thinking, okay, each of these is a linear structure except we have electrons like around them. So it's like, okay, so how are any of these linear? And the reason why one of these is actually linear is because of how they kind of deflect each other relative to like how the peripheral atoms are deflected as a result of the electron pairs. So if we open up like a Vesper chart, can just visualize what's going on here. Let's see how good quality this is. Okay, this is kind of low quality in terms of just like the pure blurriness. I'll see like this I can work with. Okay. So this is perfect. So we see here that we have a total of two peripheral atoms and two valence electrons. So this is called an AB2E2 structure, which is going to look like the structure right over here. So these two electrons are going to cause so much of a bend that these get deflected like really close to each other. So it's not going to be anywhere near linear. And if we look at these three structures here, this is an AB2E, which is going to look like this. This is also going to be bent. And this is like sort of similar to how like water bends. Like this molecule right here is just like how H2O bends because the oxygen has two electron pairs, like lone electron pairs. This AB2E structure works similarly. But if we look here at our AB2E3 structure, we're going to get, where's AB2E3? Right here. Because the idea that's going to happen is that it's important to kind of remember this like T-shape thing. I think remembering the T-shape makes it easier because the two electrons cause these three molecules, these three peripheral atoms to be in a T-shape. Then all we're doing is when we change one of these peripheral atoms to an electron pair, it substitutes this one. So then these two are just directly in line. So if you want to draw this out more accurately, it would be something like you'd have the CL here, you'd have the CL here, and like I don't really remember directions too well, but you'd have like some pair here, some pair here, and then you'd have some pair here like that. And that would cause these two CLs to be linear to each other. So then that would make our answer E here. And this is again just a pure memorization thing. And then it's especially a good concept to know because none of these structures ended up being AB2. It was some variant of AB2 that was still linear. Mhm. Okay, for C10, equal volumes of zero point 0.1 molar sodium acetate and zero point 0.1 molar acetic acid. No, this is a sodium acetate. Sorry, this is what is COOH? I'm like forgetting. Wait, C. Oh, it's a carboxyl group. So I guess this is just NaCOH. Sodium formate. Okay, so yeah, sodium formate and formic acid was resulting in pH. So you may be thinking here that, oh, if we have the same amount of uh some acid and its respective weak base, they should cancel each other out. So our pH is just 7. However, this doesn't really work because of how equilibrium works on weak acids. If this was like, for instance, like sodium chloride and hydrochloric acid, then it should end up working out. But the thing is that because this is a weak acid, we have to end up using what is known as the Henderson-Hasselbalch equation, which states that for some weak acid, I'm gonna double check this in a sec, that this is going to be equal to the pKa, which is related to what's called the acid dissociation constant, plus the log of trying to see, hopefully I remember this right. It should be the ratio between the conjugate acid and the acid itself. I'm gonna double check this. Henderson fossil block. Yeah, so the ratio between the uh what I say, the conjugate base and the acid itself. So in this case, since we have zero point 0.1 of each, this ratio ends up being 1, and thus our pH is just going to be equal to our pKa. If we look at our formula chart, we see that the Ka is 1.8 times 10 to the negative fourth. And we can use the logic that, oh, if our pH is going to be the negative log of our hydrogen concentration. So suddenly if we take the negative log of 1.88 negative 4, 3.74 is going to be our pH. Okay. Which of the following solutions is magnesium hydroxide most soluble? And this kind of comes down more to those what's it called? Those equilibrium reactions. So you have MgOH2. When this eventually dissociates, we're going to get uh the Mg2 plus ion plus, let me kind of like separate these out somehow, plus two OH minus ions. So what we notice here is that if we add water, water isn't really going to like help us with anything. And if anything, the small like dissociated hydroxide ions that exist in the water are going to add stuff to our product side that's going to end up precipitating magnesium hydroxide, which we don't want. Same thing happens to a way bigger extent when we have sodium hydroxide. We have so much hydroxide on the right side that's going to shift left. If we have magnesium nitrate, similar things going to happen. We have so many magnesium ions that's going to shift left. But uh, if we have nitric acid, what's going to happen here? So if we have nitric acid, then any hydroxide that dissolves or dissociates is going to immediately react with the nitric acid, right? Once this reacts, this hydroxide is gone. So now there's an imbalance on this side that causes the magnesium hydroxide reaction to shift right. So magnesium hydroxide is going to create some hydroxide. Hydroxide reacts with nitric acid. Now we're depleted of hydroxide, so we're going to make more hydroxide and so on and so forth. So that ends up making D the correct answer. Okay. Standard potential of the above reaction is 0.249. What is the potential? Okay. So two important things to remember that makes this one super easy. Number one, potential of a reaction is just going to negate if you flip the reaction. So if we replace all these twos with ones, these are just flipped reactions. So it would be negative 0.249. Second thing is that potential is an intrinsic property. So these coefficients actually don't mean anything. It's the same idea that, for instance, like if I had like trying to think of something. If I had like a bucket of water versus like 20 gallon, like yeah, a bucket of water versus like a bathtub full of water, they're both going to be transparent. It doesn't change anything. So in a similar idea, this electric potential is always going to be standardized at an intrinsic value, which makes our answer negative 0.249. You would not double it to get C here. Okay. Uh, water. I'm gonna pause this real quick, grab some water, and then I'll be back. Yeah, I'm back. Let's run this back again. So C13 is just going to be about trying to see, can you write out this combustion reaction in the first place? So any combustion reaction is going to start out with our hydrocarbon. So C3H6O. We need to add heat as well as oxygen gas to it. And what this is going to end up producing is it's going to produce gaseous carbon dioxide and water vapor. Okay, so now what we have to do is we gotta balance this reaction out. And the way I always do it is like this. Since we have three carbons on this side, we need three carbons on this side. And since it's the only thing that's gonna give us it, we put a three here. Similarly, we have six hydrogens on this side. We need six from this. And since each water molecule has two hydrogens, this is also going to be three. Now, on our left side, we have one oxygen. And on our right side, we have six plus three, nine oxygens. So we need eight more oxygens out of this. So we have four molecules here. Uh, and then in the case where one of these ends up being a fraction, just double all the numbers if necessary. So this becomes our reaction, and we have 4 grams of acetone. Now, if we take 4 grams of acetone and convert this into molar, like moles, we get 4 divided by the total molar mass, which is going to be H6O, 6O. This is because our molar mass, or no, or sorry, our number of moles. And we say that this amount of moles is going to create, we're focusing on the water. So every mole of this produces 3 moles of water. So this is how many moles of water we have. And multiplying this by the molar mass of water gets us 3.72 grams of water. Now, according to our handy dandy formula chart, we see this value right here, or enthalpy of vaporization, which is basically the change needed per gram of water to turn it from liquid to gas or gas to liquid. The same thing exists for fusion, which is the solid liquid change. So in this case, we need 2,260 joules per gram. So if we take this as our number of moles, or sorry, as a number of grams, multiply the 2260, you get 8,400 joules, which gets us right here. Okay. C14, frequency of light that has a wavelength of 590 nanometers. This is as easy as just remembering F equals C over lambda. F equals C over lambda. And then when you write this out, you just get that the frequency is going to be 3 times 10 to the 8th divided by 590 nanometers, or 590 times 10 to the negative 9. So you get 5.08 times 10 to the 14 hertz. Piece of cake. The important thing to remember is that it's going to be this. You have to remember the nanometer conversion, or else I think if I don't put the nanometer conversion, you're going to get the other. Yeah, you end up getting A instead of E. So remember the nanometer conversion. Okay. C15, which of the following is true about viscosity? Where's my phone? Because this one should be this should be C, I think. I remember right this. Yeah. Okay. So I remember when I first read this, when I first read this one, because I did try to read this a bit beforehand. I did originally want to pick A, but the thing is that viscosity is not a measure of how free flowing a fluid is. It's actually the measure of the opposite, how like sticky or how resistant it is. So a higher viscosity is going to mean that it's going to be like a lot more like thick, kind of like if you're comparing something really thick, like oil, I guess. Oil is really viscous. But then like free flowing water is gonna be like very like low in viscosity. So A becomes wrong. B, viscosity generally increases with increased temperature. If you increase like a liquid, it should usually become like uh easier to flow. So this one should be wrong. Let me yeah, viscosity should be just resist is the resistance. So yeah, if you increase temperature, it's gonna likely be like less resistant. C, viscosity is related to the strength of the intermolecular forces, which is true. If the forces between molecules are strong, that's going to cause you to be more resistant. And that ties into answer B, because if temperatures increase, these molecules are going to get weakened. So we're going to get less viscous instead of more viscous. For option D, fluid high viscosity flows easily. Again, this is just wrong. A and D both relate to each other, so you can tell those must be wrong. And E, long chain molecules have lower viscosities. Long chain molecules tend to have more opportunities for more bonds and like more like IMFs between them, which is going to cause them to be more resistant. So it's going to have higher viscosity. Okay, C16. Y'all can read 16 and 17. My throat is like parched from all this talking. Okay, so when we react magnesium and oxygen, we just need to be able to write out the equation for this. Magnesium and oxygen both have like +2 things. So we have Mg plus. Oh, and actually, what's important here is to realize that we're not going to react Mg and O. We're reacting Mg and O2, and that causes us to create MgO. And then when we balance out the coefficients, we end up getting this. Okay. So the way I like to do these problems is think, okay, so let's start with our first compound. So we have 5 grams of magnesium metal. So 5 grams divided by our molar mass. This is how many moles of magnesium we have, right? Now, for every 2 moles of magnesium, we need 1 mole of oxygen gas. So this is how many moles of oxygen gas we need, or multiplied by 32. This is how many grams of oxygen we need. So we notice that for 5 grams of magnesium, we only need like 3 grams of 3.3 grams of oxygen, which we do have. So that means that we're not limited by our oxygen because we have enough of it. What we are limited by is our magnesium. So that makes our answer only either B or D. And because we are limited by our magnesium, we go based on the magnesium for how much we can make. Because if we went off the oxygen, we'd be assuming we have enough magnesium. If magnesium is a limiting reagent, we don't have enough of it. So we say that with that same 524.31, every 2 moles of Mg make 2 moles of MgO. So we already have the number of moles needed. And then multiplying this by the molar mass of MgO, we get that we make 8.29 grams of magnesium oxide, with magnesium being our limiting reagent. Okay, C17. This one, honestly, even if you don't know chemistry, you can probably figure it out. We're just saying that that 3.35% of chromium isotopes, for example, have a molar mass of 50, and so forth for 52, 53, and 54. So all we have to do is just multiply all of these together. So 50 times 0.0335 plus 52 times 0.8379, then adding the other two values, we get 52.08 AMU as our answer. Okay, C18. Which of the following errors could occur during a titration of KHP that would cause the molarity of NaOH to be too low? So we're titrating our acid here. So that means that, so basically the idea here is that we have a weak acid and we're just going to add bits of NaOH slowly at a time until they all completely balance out. So once it's titrated, the number of moles of KHP should equal the number of moles of NaOH. So let's see. So in option A, we're saying that our sample of KHP was over titrated. That means that we added more NaOH than we needed to, which means that so for instance, let's say we had, so we're saying that we know the molarity and the amount of KHP that we have. And we know the amount of NaOH that we're going to be adding. Like we can just measure that, but we don't know the molarity, which is why we're titrating. So let's say two mol we have a 2 molar solution of KHP. So this is our KHP. And let's say it has 0.1 liters of it. And we have to note that when we multiply these two, we get the number of moles of KHP. And in theory, the number of moles of NaOH should be the same by definition of titration. They should cancel each other out. Well, I guess at least in this case, if it's like we're assuming it's a 1-to-1 thing for simplicity. Then let's say for NaOH, it was very similar. We said that we'll say that in actuality, this is a 1 molar solution, and we should have needed 0.2 liters. Okay. In the first case, if our KHP is over titrated, that means that we added too much of this. Okay, and we're saying that this is kind of our question mark. So we're saying that in theory, 2 times 0.1 or 0.2 should be equal to 0.2 times our question mark. So the issue that arrives is that if we add too much of NaOH, this value right here becomes too big. This value is going to increase, and then as a result, this value decreases. So that causes our calculated molarity of the sodium hydroxide to be too low. So A looks really solid, but let's check the other answer. The KHP has not been dried prior to using. So if the KHP has not been dried, that would mean that, what would that mean? That would mean that the actual, let me think, because the number of moles should still be the same, even if it's not dried. So it should mean that when we measure like the volume of the KHP, this amount right here is actually going to be bigger than usual, right? And we would be adding the same amount of NaOH. So if this value became bigger, then this value would also have to increase. Because we're saying under the fact that even though it is a 2 molar solution of KHP, we don't know that because it didn't dry, it's actually less than 2 molar. So we're saying that okay, we think it's 2 molar, and we have a slightly more, the volume that we measured is slightly more. So we would end up calculating that with the same NaOH, we would need a bigger molarity. So that makes B incorrect. See, the KHP stuck to the weighing paper when it was being put into the flask. So that would mean that we actually, let me think. That would mean that we have less moles of, see would mean that we have less moles of KHP actually in the solution. So even though we're saying that this is our molarity here is actually smaller and we have less moles. So we're going to end up adding less of this, and we're going to think that, oh, if we had less of this for a 2 molar solution, we must have had a higher molarity. And these explanations I am realizing are like pretty bad. But there's that. I feel like someone's about to like knock on the door. Then for D, we have the KHP didn't fully dissolve while titrating. So dissolution shouldn't really affect it too much. And what's going to happen there is that that shouldn't really affect how we have the KHP change. And then E, the KHP was dissolved in 60 milliliters instead of 50 milliliters of distilled water. So I did say like 0.1 and 0.2 liters, but we'll say that that's like the same thing. So if we have, if so we didn't realize here that the 0.1 is actually more than 0.1. And what's gonna happen is that we should be adding the same amount of stuff here. So we're gonna be thinking that, oh, if we had this amount, if we had this, we had only this amount of solution, then that means that our molarity must have been way bigger. In reality, this value was bigger, so then this value would be like smaller and matching the actual amount. Okay, so now yeah, honestly, on this one, explaining A was easier than explaining why the other ones are wrong. But honestly, for these kind of like titration setups, it's way easier if you've actually done titrations before because you kind of just see like how all the variables relate to each other. Okay. In which molecule is the C to C bond the shortest? Okay, so if I'm seeing which bond is going to be shortest, this is making me thinking this is going to be something to do with single, double, and triple bonds. Triple bonds are going to be shorter than double bonds, which are going to be shorter than single bond. And the same thing works with strength. A triple bond is going to be the strongest because it's so close and short. So C2H2, if I remember right, actually, I'm not even going to bother drawing this out. I'll just show y'all the Lewis structures for these. So you see that in C2H2, once we draw this out, we get this triple bond here. So that's like big, big information for us. That tells us that, okay, this must be a super strong bond. But is there any other triple bond that could for some reason be stronger? If we look at C2H4, Lewis structure, we get the C2H4 ends up being a double bond. And then C2H6 should be a single bond like that. C2O42 minus, so the oxalate ion. Our oxalate ion is also going to have a singular bond, you can see here. And then C2H3O2. So this is the acetate ion. And that's also going to have a single bond between the two carbons. So once you draw these all out in context, you would realize that C2H2 is the only triple bond, and thus it's going to be the shortest molecule. Okay. And yeah, I did get this one right. Okay, so it's good. Then 20, don't ask me why this is question 20, but I'm so glad that this is like the last one here, which was the alkaline earth metal. Alkaline earth metals are just this second column right here. So we go through the list and we see that our answer is just going to be calcium. Sodium is going to be an alkali metal. Iron is a transition. Lead is a transition, I think. Or lead is, I guess, metalloid. No, not metalloid. It's a post-transition. And then uranium is considered an actinide, I believe. Where's uranium? Yeah, right over here in the actinoids. And yeah, that is all the questions. Yeah, I guess there were like one or two explanations that were kind of bad, but hopefully that makes a lot of sense. In my opinion, I think chemistry is pretty easy to improve in. I know, at least from like an Allen perspective, not a lot of people were like really strong at chemistry. So I kind of just took advantage of that, try to like learn it because it clicked for me really fast. I think if you have a similar experience, definitely go for it. Really easy section that I think can help you boost your score. This and physics. And yeah, I honestly don't know what I'm gonna do with my next video if I ever or whenever I have a next video. But yeah, thank y'all for listening and see y'all next time.